Hi everyone, in today's lesson we're going to look at how we can use the derivative of a function to find the equation of the tangent at any given point on the function. Now previously we learnt that the derivative of the function, dy dx, is the gradient of the tangent of that function. So if we picked any position on a curve and we found the tangent there, then we know that that function of the tangent is dy dx. And we can see that on this curve, we're in that positive section, the gradient's positive. And if we looked at the other side of the curve, then our gradient would be negative. But it's all following this one function. And the derivative is going to be what that gradient is equal to. So if we wanted to look at this function in particular, we've got the function here, y is equal to x squared. So dy dx using our power rule would simply be 2x, and when x is equal to 1, then dy dx is equal to 2. Now if we plotted our function, gradient of the function curve here, so we've got dy dx is equal to 2x, then we could see that what we actually have is passing through 0, 1, 2, 2, 4, and we can draw our line passing through those points there. And we can see that at this position here of x is equal to 1, we have parallel lines because our gradient of the tangent is equal to our function. Similarly, if we think of it in terms of where we are on the curve, if I look at this position here, the gradient of the tangent, we can see, is quite steep and would be equal to 4, just as our function of the gradient is also 4 at that location. So we can see there's a relationship between those two. We also know that a tangent is a straight line that touches a curve, which means we have a linear relationship. So we know that the rate of change of a line is determined by its gradient, and that all lines with the same gradient are parallel, which means if we know one point, we can find the equation using the point gradient formula. So y minus y1 is equal to m outside of x minus x1, where x1, y1 are our known points. This means that if we put these concepts together, we can find the equation of the tangent at any given point because we know the location of that point, because we have our position on the curve, and we've got the gradient, or we can find the gradient by deriving our function. So this means that we can find the coordinates of the point by substituting x value into the original equation. So we can find x1, y1, and we can differentiate to find the gradient, which means we have all the information we need to use the point gradient formula. So let's consider what this would look like by completing an example, a couple of examples. So we have a parabola, y is equal to x squared plus 2. So we have our general parabola there, and we can see plus 2 means we've got a vertical translation of 2. And we want to find the gradient of the tangent to the parabola at the point 1, 3. In other words, we are finding the gradient of the tangent at this point here. Now, in this case, we don't need to substitute in because we've been given the point, which means all we need to do is find the gradient to find the equation of the tangent. So our function was y is equal to x squared plus 2, which means using the power rule, our gradient function will be dy dx is equal to 2x. So substituting x equals 1 in, because that's our x value for our point, we know that our y dx, or our gradient, is going to be equal to 2 times 1, which is 2. So we have our point in our point gradient form, and we have our value for our gradient. So that means to find the equation of the tangent, all we need to do is substitute our values in. So our point gradient formula, y minus y1, is equal to m outside of x minus x1. So y minus 3, which is our y1 value, is equal to the value of the derivative there, which is 2, outside of x minus our x1 value of 1. Expanding the brackets out, 2x minus 2, in the 3 across, we'll get y is equal to 2x plus 1. So here we have our equation of the tangent at y is equal to, at the point 2, 3, and we can see that lines up. We have the y-intercept of 1, and we see we have a increase rate of change of 2. So